Proceeding on, these are questions number 7 and 8 in the fall 2018 1141 final exam. All right, so this question is question number 7. The amount of gas that occupies 36.52 liters at 68 degrees Celsius and 672 millimeters mercury is blank moles. Okay, so there are a couple things that you have to recognize about this. The first of which is this is talking about a gas, and what that likely means whenever you're defined with a volume equals 36.52 liters, a temperature, this ultimately is probably dealing with the ideal gas equation, and the ideal gas equation is PV equals nRT. What you have to do with this question is manipulate this algebraically in order to figure out what we're actually trying to solve for. This says blank moles, okay? What we want to do whenever we see an ideal gas equation problem is we want to make sure that the units that we're talking about are the units that we need to solve for. Okay, so, or the units that we're provided with are the ones that we want to use. Okay, so volume is going to be measured in liters whenever you're talking about the ideal gas equation. Temperature, however, is not going to be measured in Celsius, but instead it's going to be measured in units known as Kelvin. So what you want to do is take any temperature that's given to you in degrees Celsius, add 273.15. This will convert any temperature in degrees Celsius into temperature Kelvin. So 273.15 plus 68, that would be 341.15 Kelvin. Okay, so now we've got our temperature in the right units. This next one is millimeters mercury. So that is going to be our pressure, because all that stems back to is the discussion of a barometer. Okay, so what you need to do is convert your pressure into atmospheres, or ATM. And you have to know the conversion. That is 760 millimeters mercury is equal to 1 ATM. Okay, and sometimes whenever you might see 760 torr, that's another unit. 760 torr is equal to 760 millimeters mercury. That ultimately goes back to 1 atmosphere. So you have all these definitions. So what we've defined and what we worked with is our volume, our temperature. We need to, however, figure out what our pressure is. Pressure is equal to 672 millimeters mercury. We need to convert that into atmospheres. 760 ATM is 1 ATM. Sorry about that, there was a typo there, and it's 760 millimeters mercury is equal to 1 ATM. When you do this conversion, ultimately comes back to something like 0.88 ATM. Okay. The last thing that you need to know whenever you're manipulating this, because ultimately what are we solving for? We are solving for N, which is the number of moles. Okay, so we can contort this equation. PV over RT is equal to N. So we did the algebra to divide RT on each side. We've isolated N, which is what we're solving for. This R value is a constant, and that is 0.08201. The units for that are liters, atmospheres, mole, Kelvin. Okay, so we can plug all that in, and ultimately the only units that we're going to be left with are moles. So now we can take our numbers. Pressure, which is 0.88 ATM, multiply that by our volume, which is 36.52 liters. Divide that by our R value, which is 0.08201, and multiply that by our temperature, which is 341.15 Kelvin. Now when we plug all of that in, what we learn is that our correct answer is, I'm going to plug this into my calculator here instead. After you plug this into your calculator, and just so everyone knows, I am a very strong believer in using parentheses on your calculator, so I'd probably plug this in as a function and divide it by this whole function right here. And what you come up with is 1.15 moles. Okay, so that's all there is to this one. Now, if you don't know the ideal gas equation, you're going to kind of struggle with this. So make some practice problems, or do practice problems like this. One thing that you also need to know, or that's worthwhile to know, is that 1 mole of a gas at standard temperature and pressure, which standard temperature and pressure is approximately 296 Kelvin, pressure is 1 atmosphere. 1 mole of a gas is going to occupy 22.4 liters. So if you keep that in mind, and then you adjust for, changes in temperature, changes in pressure, as well as changes in volume, it's going to help you out with this sort of problem. But know this ideal gas equation. I'm going to put a box around the ideal gas equation in yellow here. PV equals nRT. All right, moving on. Question number 8. Question number 8 reads, the enthalpy change for the following reaction is negative 483.6 kilojoules. 2H2, we got a 2 coefficient out in front of our H2 gas, plus O2 gas, there's a 1 coefficient in front of that O2, yields 2 H2O gas. Therefore, the enthalpy change for the following reaction is blank kilojoules. Okay, so now what makes these two different? 4H2 plus 2O2 yields 4H2O. All the phases are the exact same. The only thing that's different is our coefficients. And if you look at all those coefficients, what's happened? What's the difference between our reaction and our final reaction? Well, it's simply a factor of 2. And if you multiply these coefficients, then you have to multiply the energy that's associated with them. So 2 times negative 483.6 is going to be, it's still a negative number, so we can do some process of elimination. The same reaction is going to have a negative value, so we can scribble out A, we can eliminate B. C shows the exact same answer. Well, if we're talking about it reacting more of a substance, well, it's going to produce more energy. So C is out, leaving us only with E and D. And if you look at E, that's a positive number, so that's out. Simply through process of elimination, we're left with D. This question is a Hess's law sort of problem, and this tells you, like, if this is the enthalpy change, negative 483.6 kilojoules is the energy associated with 2 moles reacting with 1 mole to produce 2 moles of H2O. Well, then 4 moles of H2 plus 2 moles of H2, that's 2 times as much. That's going to produce 2 times as much water. It's going to produce 2 times as much energy. All right, well, I hope this is helpful. I'm going to move on to some more problems in just a moment.